recording started. My name is Kyle Dayton. I'm a PhD candidate at Cornell University in New York, and the title of this talk is Revealing Magma Reservoirs, the Role of Mountain Fluid Inclusions in Understanding the Eruption of Tajogaite, La Palma in 2021. There are two main focuses of using this recent eruption, and our main goals are to understand, can we use CO2-rich fluid inclusions to locate magmatic reservoirs via Raman spectroscopy? And also, how does fluid inclusion barometry compare with other data, including mountain inclusions, MT studies, seismicity, deformation? How does this renewed technique of using Raman spectroscopy compared to other methods of barometry, and what can we use these fluid inclusions to help us uncover the pre-eruptive and synterruptive processes within these eruptions? And if you're interested in any of this work in more detail, there are two publications that I will be discussing today that are out in G-Cubed and Science Advances. So let's give ourselves some geologic context. The Canary Islands are an archipelago off the northwestern coast of Africa. They're closest to Morocco and Western Sahara. The archipelago sits on the oceanic crust to the west of Africa, with the transition between oceanic and continental crust somewhere to the west of the easternmost islands, Lanzarote and Fuerteventura. Compared to Hawaii, these islands are significantly older. The oldest of the Hawaiian islands, Kauai, is only 5 million years old, versus the oldest still exposed Canary Islands are over 20 million years old. So there's plenty of geologic time and eruptive history preserved on these islands. We will be focusing on La Palma, which is the second youngest of the islands on the western end of the archipelago, focus where most of the historical volcanism in the last few hundred years has been centered on. The Canary Islands are also on a very slow-moving African plate compared to the Pacific plate, which is moving almost 3 times as fast. So the archipelago is still active and also still exposed due to the rigidness and the age of the oceanic crust that these islands are on. So what is a typical Canary Island eruption? So overall, the historical eruptive record of Canary Island volcanism begins in the late 1400s, and there has been volcanic activity on many islands. Of one is Tenerife, where the summit Teide. Tenerife is the center of the archipelago, and there's been several eruptions there. We also have a submarine eruption, El Hierro, which was the last volcanic event prior to 2021. And then we have La Palma, which on the Cumbre Vieja Rift, which is the southern tip of the island, has been the focus of the seismic activity. Overall, a typical Canary eruptions, on average, they occur every 30 to 35 years. Duration-wise, they're typically about 50 days, with one noticeable outlier. There was also an eruption on Lanzarote, one of the easternmost islands, that lasted for 6 years. But most of this activity has been focused on La Palma, and that event, though, is a little bit significant in its duration. The 2021 event lasted for 85 days. So why is there volcanism on both sides of this archipelago? Unlike Hawaii, where the volcanism is focused to one end of the archipelago, there has been historical volcanism on both ends of the Canary Islands. There's been many different techniques and models used to explain this bimodal volcanism on both sides of the archipelago, with one of the proposed reasons for this is a edge-driven convection due to the cold African craton, where you have upwelling hot mantle material deflected through the continental crust in a lateral channel, supplying magmatism to the westernmost of the Canary Islands. But we're focused on La Palma, which is more directly under the current position of the mantle plume. So let's go back to La Palma. So here's an image of the cone on La Palma. This was in October of 2021. The cone is centered on the Cumbre Vieja Rift, and these are images of the area of Las Manchas just a few weeks into the start of the 2021 event. So some social impacts of this event. This was the most well-monitored canary eruption due to its occurrence in the modern day, with an abundant seismic network with significant monitoring of the area before and during the event. The evacuation of over 8,000 people was significantly larger than the two previous on-island eruptions in La Palma. The last event on island in the Canary Islands was in 1971, just on the southern tip of the Cumbre Vieja Rift. I don't know if you can see my mouse. It's in brown here, just at the southern tip of the island. Prior to the 1971 event, there also was an event in 1949 that was only a few kilometers away from where the 2021 cone opened. If you look at the population density map, you can also see that the two main population areas of La Palma are also centered on the Cumbre Vieja Rift and are susceptible to lava flows and volcanic hazards that will be an issue as the population of the isle continues to grow. This was a pretty significantly destructive eruption with over 3,000 buildings lost, 70 kilometers of roads, and a significant amount of damage to crops and farmland, with €1 billion in damages. But because of the very significant and well-studied monitoring of this eruption, there was no direct loss of human life. So this is a Google Maps image to get an idea of the extent of the lava flows. This is the area before the eruption. And then this is the extent of the lava flows, which did reach the ocean in two places throughout the 85 days of the eruptive activity. So what did the eruptive products look like, and what did we use for this study? In order to constrain volatiles of melt inclusions, we want to focus on rapidly quenched material in volcanic tephra. So ideally, our grain size is below 2 millimeters to allow for really rapid quench of melt inclusions to ensure that they're glassy and that there's not a lot of hydrogen diffusion lost during this quench. So on the left is the stratigraphic section of samples that we used for this study. The green stars represent samples that we used for fluid inclusion studies, and the blue and red circles and triangles are melt inclusion samples. And due to the really detailed work in Romero et al. 2022, and some of our eyewitness records of different layers of the eruption, we were able to constrain some of the dates of this tephra section to constrain the evolution within the eruption itself. So the earthquake record, where is the magma? There had been seismic precursors for the La Palma 2021 event starting in 2017. This eruption was forecast with evacuations occurring before the cone opened, minimizing the damage. But where is the magma actually stored? Through these many different earthquake swarms, we wanted to understand what would the fluid inclusion record tell us? Is there a chamber that is constraining where this magma is stored? And will these fluid inclusions show us if the magma is stored in a deeper magma chamber or more of a shallow magma chamber, as there's both seismic activity throughout the eruption in both of these chambers? So why do we care about barometry? What can barometry tell us? So constraining magmatic reservoir depths is essential to fully interpreting a volcanic system. And the geochemistry of eruptive materials preserve information on conditions and processes at depth. But commonly used mineral melt barometry is limited by high degrees of uncertainty, up to 8 to 10 to 20 kilometers. So on the right is a schematic diagram of a magmatic chamber, and with some CPX barometry, the error bars are rather large, and it would be hard to determine if your magma and your crystals were stored at maybe 5 kilometers or 15. So we wanted to develop a new technique or use a technique that's been developed and constrain it more to use fluid inclusions to identify where magma is stored as precise and accurately as we can. So how are we going to look at that? We're going to use melt and fluid inclusions. So why melt and fluid inclusions? They are present in nearly all geologic environments. They preserve chemical and physical records of geologic processes, and inclusion petrography allows, to some degree, a temporal evaluation of the processes that are occurring within a single phenocrust. So all of this work was done on single crystals, polishing individual crystals, and identifying different planes of fluid inclusions and melt inclusions to constrain what happened in these magmatic systems. Before I talk more about melt inclusions, on the upper left-hand side of the slide, there is a cutout image of a melt inclusion. And this inclusion essentially consists of two parts. There's a light brown silicate melt inclusion, and inside that inclusion is a darker sphere or circle. That is a melt inclusion vapor bubble. And within that vapor bubble, particularly for La Palma, which is a very CO2-rich eruption, there's a significant amount of CO2 inside of that bubble that we essentially treat as a fluid inclusion. On the right-hand side of the slide, the sort of diamond shape, that is a cutout of a fluid inclusion. And in the case of La Palma, it contains CO2. So we will use Raman spectroscopy to account and quantify the amount of CO2 in the melt inclusion bubbles as well as the fluid inclusions. Okay, so melt versus fluid inclusions, two different types. They both have pros and cons. And anyone who has conducted melt inclusion studies will know the life cycle of an inclusion is rather lengthy and rather expensive. So for melt inclusions, you need several analytical techniques. You would need Raman spectroscopy to account for the CO2 in the vapor bubbles, if that is something your system has. You then would need to polish your samples again and use SIMS, either secondary ion mass spectrometry or FTIR, and wait for your inclusions to measure the CO2 and the water within your glass. Then you would need another analytical technique, EPMA for major elements, and then subsequent LA-ICP-MS if you're interested in trace elements or constraining oxygen fugacity. With all of that information, you would reconstruct the volatile budget of your specific inclusion and use a solubility model for an estimate of entrapment pressure. And through all those steps, the error of melt inclusion analysis and reconstruction significantly larger. Of course, that leads to much more chemical information that you can glean from inside of your melt inclusion. It's pretty much a choose your own element analysis of whatever you'd like to look at for your melt inclusion. Fluid inclusions are simpler to analyze. You would either just need Raman spectroscopy or microthermometry to determine the density of your CO2 fluid. And then you could use EPMA to get an estimate or a measurement of the composition of your inclusion host to get temperature. Using your density of CO2 and your crystal host temperature to constrain temperature, you would then use an equation of state, which has a significantly less error on it than a solubility model. But fluid inclusions preserve less of that chemical information present within melt in your magma chamber. So why fluid inclusions now? Fluid inclusions and melt inclusions have been described for hundreds of years. This work, and particularly one of the most cited descriptions of melt inclusions, were back in the 1850s. And Edwin Roeder pioneered the use of fluid inclusions in volcanic materials back in the 1980s. So why are we focusing on them now if this has been done before? So most previous fluid inclusion analysis had been done with microthermometry. So this image on the left is a microscope with a Lincoln stage attached. You would then take your crystal or your thick section, put it in the Lincoln stage or modified gas stage, quench it, cool it down, freeze with liquid nitrogen, and then observe the phase transitions of your specific fluids inside of your fluid inclusions. This can be slightly difficult, can be limited by optics if you have very small inclusions. It can be difficult if you have low density inclusions. And you also have a slightly more limited view of the chemical information inside of your inclusions, as you will not get a spectra of an in situ daughter crystal inside of your inclusion or detect what species of trace gases are present within your inclusion. So we are using a refined Raman technique, which can help get over some of these issues dealing with limitations by optics. You'll be getting a spectra of the actual chemical components inside of your inclusion itself, and you will not have to observe the phase changes at specific temperatures, which is very much an art and is more difficult to learn than using this Raman spectroscopy method, where scientists can come and use the instrument with more limited training. So to get an idea of what is inside these inclusions, this is a video of fluid inclusions from La Palma. These are lower density inclusions than most analyzed for this study, but to give you an idea, they have two phases of CO2, both in a liquid and vapor. And then in this video, I'm heating up the inclusions, and you can see the homogenization of these two phases. So I'll play it now. So there's two phases. You can see the different fluids moving around. And at one point, those two different densities of CO2 will homogenize into a supercritical phase. This is important for microthermometry. At this temperature change, you would record what temperature it is. They homogenize there. And for Raman spectroscopy, it's important that you're only measuring a single fluid and not two different fluids at the same time. So here is an image of the Raman spectroscopy system at Cornell University. So we are using CO2 barometry. Our olivine inclusions are glued to a slide on a thermoelectric Peltier plate that we control. So we heat our inclusions up above that critical temperature of CO2. So we do not have to worry about having two different densities of CO2 fluid in the same inclusion. So we're measuring one density, which helps greatly with the error and precision of our inclusions. We also are using a neon lamp to address the nonlinearity of the Raman shift, and we are able to measure CO2 in inclusions down to a micron. So that is pretty small. Pretty much if you can see an inclusion with a 100x objective, we can get CO2 density out of it. On the right, the Raman spectra of CO2 is broken into two peaks called the Fermi dyad, and these are proportional to density. So we'll use the split of the Fermi dyad, and we have specific equations for that to account for the density of the CO2 fluid. Just to look at the phase diagram, the inclusion on the upper left, that's a picture of a two-phase fluid inclusion at room temperature, somewhere on this line where you have both a liquid and vapor coexisting, just to highlight that we heat up to 37 degrees C to ensure a homogeneous fluid. The inclusion on the right is a much denser inclusion trapped as a supercritical fluid inside the magmatic chamber around 1200 degrees C. So how do we convert from density, from our Fermi dyad splitting to density? There is a densimeter calibration specifically for the Raman at Cornell. This calibration is published in DeVitri et al. 2021. And this fluid density calibration apparatus is a specific cell that we use to obtain equations specifically for the Raman spectrometer that all of these studies have been used. And if you look at the line compared to other literature densimeters, this calibration has much less deviation in density difference within that miscibility gap, where there are two phases of CO2 present within fluid inclusions or amount inclusion vapor bubbles. Using this densimeter, we then can propagate error on our fluid inclusions. On the right is a plot of our fluid inclusion error. So that orange square is a fluid inclusion with, we're accounting for plus or minus 50 degrees C and temperature error. And those are the error bars with the densimeter calibration compared to the 1 sigma calibration data and a 1 sigma test data for CPX barometry. So the fluid inclusion method of identifying pressure has significantly less error. So back to La Palma. We went through some of these methods, explained what we're doing. Let's see what these crystals erupted during 2021 are telling us. And inside this crystal, we have both a pretty large mount inclusion and a fluid inclusion as well. So earthquake evolution during the La Palma eruption. Prior to the start of the eruption, starting with the unrest on September the 11th, 2021, with the opening of the cone, two main earthquake swarms were developed and continued for the duration of the event. A shallow earthquake swarm around 10 kilometers and a deeper earthquake swarm around 25 kilometers. And we were curious to know, is the magma that's driving this eruption, will these fluid inclusions record this deeper chamber or this shallower chamber where magma is sitting? Once we analyzed our fluid inclusions, on the left is an example of a primary fluid inclusion in an olivine phenocrest. We were able to identify that these olivine record a consistent mantle storage depth throughout the duration of the eruption. So the moho under La Palma is about 14 kilometers, and we found that the olivine MG number increases with time and is also recording a pulse of primitive magma that drove the eruption. And we also see that the fluid inclusions with our error bars show that magma depths and where these olivines were stored increased slightly as the eruption progressed and increased with an increase in magnesium number. So those are our fluid inclusions there with the samples from left to right. Plotting the earthquakes in 3 dimensions with fluid inclusions, just with depth, because we do not have latitude and longitude for our fluid inclusions. We were able to see that these fluid inclusions, primary fluid inclusions in olivine, align with the deep seismic swarm for the La Palma 2021 eruption, indicating that this magma is stored in the mantle. So we were curious to understand, is this unique to the 2021 eruption, or is this just a reactivation of a magma chamber that has been in process in the Cumbre Vieja rift for years? So looking at some literature data from microthermometry, there has been significant work on different mineral phases in xenoliths, and those xenoliths are all recording shallower pressures in the aligning with the upper seismic swarm, while work on phenocrysts for olivine, also from the 1949 eruption, record the same pressure within error of the 2021 eruption, indicating that the 1949 magma chamber and the 2021 chamber are is rejuvenated for the 2021 event. We also found that clinopyrexene, even though there are clinopyrexene inclusions within olivine hosts that record these deeper pressures, all clinopyrexene phenocrysts and fluid inclusions that we also analyzed with the Raman spectroscopy technique also record shallower depths. Now, if that is an issue with clinopyrexene being a less structurally sound host than olivine, maybe, but we also found with clinopyrexenes from the 2021 eruption, they're recording shallower pressures. So we've learned about the fluid inclusions and what they're telling us. What about melt inclusions? So in this image, in the center of the crystal, this is a focus stacked image. So the inclusions appear at the same level, but they are not. There's 2 melt inclusions on the left and the right. Both of those were analyzed and fully reconstructed for CO2 budgets. And we also identified that inclusions on the left, these bigger, more wrinkled inclusions, record pressures up to 10 kilometers deeper than one of these more degassed, rounded melt inclusions on the right. And we also can see that there are CPX inclusions inside olivine erupted towards the end of the eruption, but not in the beginning. So what do these tell us? So is there a geochemical variation with this magma recharge that was identified for the 21 eruption? We find that both melt inclusions from the start and end of the eruption, they're all basinitic. They're all in the same classification diagram. Essentially, the magma is very homogeneous throughout the duration of the event. But the largest change in major element composition was the calcium-aluminum ratios, and a inflection point that was identified in the lavas studied by Day et al. In a mid-November point, we can see that there are two groups of calcium versus aluminum ratios that cluster with our melt inclusions, recording lower and then subsequently higher ratios towards the end of the eruption. So does this magma recharge affect magma storage reservoirs? Here is a diagram showing the CO2 versus H2O of all of our melt inclusions, and we can see through these reconstructed CO2 budgets that this recharge did not have a great effect on the magma storage. And this was also reflected with the fluid inclusions, that they did show slightly deeper depths as the eruption progressed, but the error bars on melt inclusion analysis cannot constrain this slight decrease in this slight increase in depth, as the melt inclusion error bars are too large to see this. Indicating the importance of vapor bubbles, particularly for the La Palma eruption. If we were to use the CO2 contents only dissolved within the matrix glass of these melt inclusions, all of these inclusions would plot above the moho and would appear to align with the shallower crustal chamber that was seismically active during this event. There is still a significant amount of CO2 in this melt, but when the vapor bubbles are reconstructed, these inclusions have over a 8% of CO2. We do find that the water contents of these melt inclusions decrease with time, and some of these later erupted, more evolved olivine phenocrysts have re-equilibrated and show a loss of water as they've re-equilibrated with the lower water-bearing primary magma. So do melt inclusions record the same storage conditions as fluid inclusions? Specifically in the same grain, we found a few inclusions, a few grains that had both melt and fluid inclusions trapped within the same inclusion assemblage. And within the same inclusion assemblage, yes, melt and fluid inclusions record the same pressure within error. So here's a good example showing the difference in error bars between fluid inclusions and melt inclusions. This crystal specifically had 4 fluid inclusions that all give similar pressures within error. And then on the right, inclusion 8 is a melt inclusion. And you can see that the propagation of error from melt inclusion analysis is significantly larger. Most of that error has to do with the volume of a melt inclusion. In order to mass balance and reconstruct a melt inclusion, you need to have a very good estimate or measurement on the volume of your inclusion. In the case of these melt inclusions, we measured the melt inclusion in a 3rd dimension. We used Raman spectroscopy for that. The Raman stage has the ability to program within half a micron. So we took the thickness of our melt inclusions using Raman spectroscopy. We'd focus, above the inclusion, see the olivine host, and then see how deep and long we would have that melt signature before we hit the olivine host again. And then to cross-check that and make sure that that Raman depth method worked and wasn't obscured by the, difference in confocality of the Raman. We then polished some of those inclusions orthogonally to confirm that our measurements in the 3rd dimension were accurate. Even with that 3rd axis measurement of the inclusions, we still accounted for over 30% to 40% error on our melt inclusion reconstruction, which is then propagated in the minimum and maximum CO2 that would be within that inclusion for those error in volume measurements. So how do our melt and fluid inclusions compare across the entirety of the eruption? Plotted with the seismic swarms for the duration of the 85-day event, we find that both melt and fluid inclusions are recording deep magma storage. Something else that we also added here, we analyzed some decrepitated fluid inclusions. So these are fluid inclusions that were trapped deeper and then decrepitated or exploded at some point on ascent. But because they're still hot in a magma chamber, that brittle deformation was then rehealed rather quickly, preserving CO2 density within some of these inclusions. And there's also two groups of decrepitated inclusions. There's ones that align more with the shallower magma chamber swarm, seismic swarm at 10 kilometers. And then there's a second group of decrepitated inclusions, which decrepitated right upon ascent, and they preserve densities right around the detection limit of the Raman spectroscopy method. So just to sum things up, mountain fluid inclusions record the same deep magma storage for the 2021 eruption in La Palma. Careful petrography of mountain fluid inclusions is essential for reconstructing magma storage. Different mountain and fluid inclusions will give you different pressures depending on their petrographic classification and inclusion assemblage. And our renewed calibrated Raman spectroscopy method can allow for the rapid measurement of inclusions down to 1 micron. For the study of just fluid inclusions for La Palma, all inclusions were found and measured, and data was processed within a week. So we were able to analyze a few hundred fluid inclusions and determine a deep magma storage occurred on the order of a few days. And I'd like to give a special thanks to Talvoca for enabling access to the exclusion zone for us to collect these samples. And I'd like to thank you all for your time. If there's any questions.
Thank you, Kyle. That was a great presentation on the Tajogaite. So yeah, we're gonna open the space for questions. You are welcome to either raise your hand using Zoom, unmute yourself, or type your question in the chat. All right, Jisoo, you can tell us your question.
Hi, thank you for a great talk. It's very interesting. I just wanted to clarify, I think I maybe misunderstood this. So, for the fluid inclusion specifically, there was some sort of rehomogenization process initially, was that right?
Yeah, so depending on the density of your fluid inclusion at room temperature, you can have CO2 in two phases. So actually, I think I have a slide showing this peak somewhere. Yeah, here. Oops. Boop, boop. So if you were to take a measurement with Raman spectroscopy of your fluid inclusion below the critical temperature of CO2, which is 31 degrees C, so it has to be pretty toasty in the room, you actually can identify two Fermi dyads of your liquid component and your vapor component inside a single fluid inclusion or mountain inclusion, and that actually obscures the true density of your inclusion because you're measuring actually two things at once. So just to account for that, the fluid inclusions, most of them are above 0.7 grams per cubic centimeter. So they're all in that either just liquid or supercritical region, but all of the mountain inclusion vapor bubbles for this eruption are within that miscibility gap where they would need to be homogenized prior to analysis. If you're in a lower density system, say Kilauea, most of those inclusions are too low density to reach that miscibility region.
Cool. So if I may, I've heard that with rehomogenization, there can be some issues like maybe like leakage or stuff like that. So how does your
Yeah,
lab go about those challenges?
so I guess that there's actually two different types of rehomogenization. So there would be like high temperature volcanic temperature rehomogenization. We just heat to 37 degrees Celsius. So there's no issue in distortion of your host or water loss at 37 C. So there's no issue with that rehomogenization versus some of the more high temperature, high pressure, piston cylinder, multi-anvil, or even a Lincoln stage at 1 atmosphere. Then if you're bringing it up to 1100, 1200 C, then you can have some issues with this. But I mean, even using like an old microscope with an incandescent light bulb, you can homogenize just in situ with a light bulb.
Cool, thank you.
All right, we have another question from Glenn. He asks if Was there any surface deformation data?
Surface deformation. There is work on surface deformation. This study did not look into that, but there is work on deformation within the 2021 eruption, if you look in the literature.
All right, any other question?
Yes, do you listen me?
We can hear you, Julian.
Okay, thank you. Kelly, great talk. I have a question about it is possible work with other phenocrysts, for example, orthopyroxene and plagiocates, for searching metal inclusion and explore this possibility.
Yes. So orthopyroxene, just from what I've seen, tends to be a little bit of a stronger host potentially than clinopyroxene. Any feldspar that I've really looked at, full of fluid inclusions. One of the reasons I love fluid inclusions is they are in every mineral, and I am really a mineralogist at heart. And if you look hard enough and are stubborn enough, that there should be fluid inclusions in any, phenocryst you're looking for in a volcanic system. You do have to be aware of what volatiles you'll have exolved in your system. If you're in, a shallower system with plagicles, you might not be in the pure CO2 part of your system anymore, and would have to use a different either technique or phase diagram, as you'll have exolved, SO2 or water vapor, as well as CO2. So just being aware of what volatile species you have, and that this method, this Raman spectroscopy, like CO2 rich fluid method, really works for deep magmatic systems. Yeah.
Okay, great, thank you.
Alan, you can go ahead.
Sure. Thanks, Kyle, for a really, really excellent talk. That was wonderful. I'm curious if you found other phases in the fluid inclusions, like any sulfur compounds or other things like that. Thank you.
Yeah. So of the around 200 fluid inclusions we found, we had traces of SO2, like very tiny traces in maybe 2. Enough that, like, if we calculated the mole fraction, it was pretty much negligible. But at these very deep mantle pressures, that was about it. There has been work on noble gases of this eruption, and there is helium detected in some of these. From work on microthermometry, also for this work, the melting temperature of CO2 was a little bit depressed, and we could say that is also helium. So there are trace gases, but with Raman spectroscopy, traces of CO2, and then sometimes a slight amount of water. But through using the volatile contents of the melt inclusions, we're still in the range where we can use the CO2 only equations of state to apply to these samples.
We have a question from Michael.
Hi, Kyle. Great talk. I was curious about your thoughts on taking this system as like would it be possible to move it into the field for like real-time analysis of samples at an eruption locality? How do you imagine that like playing out, or is it possible, or are there more kind of like applicable ways of getting real-time data for studying volcanic eruptions, as they're happening?
Yeah, so there's been more than several other research groups who are interested in using fluid inclusions as a rapid barometric technique, using either microthermometry or calibrated Raman spectroscopy method. I think the issue with that is you need to either bring a Raman spectrometer into the field or have a source of liquid nitrogen for microthermometry. And if you can do that and bring your Raman or your Lincoln stage to the field and to the active volcano, you can get them in, an hour. If not, it might be easier to mail samples to a lab that has the instrumentation there as well. Unless field Raman spectrometers get really good. Yeah.
All right, one last question maybe. Okay, seems like we have no more questions. Thank you everyone for joining. Thank you, Kyle. That was an amazing presentation. So I just want to remind everyone that our next session in 2 weeks is not gonna be at 4 p.m. UTC. It's gonna be at 10 p.m. UTC -4. It's gonna be at 10 p.m. UTC -4. That's to accommodate our speaker, Anki, who is in Indonesia. So for those who are on the other side of the world, it's probably going to be easier to attend this session. And yeah, thank you everyone. I'll see you in 2 weeks.
Thank you.